Hello everyone, my name is Todd Richards. I'm a senior bioengineering major, and I will be talking about my research on the interactions between polypyrrole and graphene oxide, which I am conducting under the supervision of Dr. Isaac McWan at Fairfield University. This work deals with the study of the interactions at the interface of graphene oxide and pyrrole in order to better understand the evolution of polypyrrole over the surface of graphene oxide during the synthesis of this film using cyclic voltammetry. Graphene oxide, an oxidized form of graphene, a carbon allotrope, has many applications in the field of bioengineering. But one of the pressing issues with carbon allotropes in general, and graphene oxide in particular, however, is that they cannot form freestanding films on their own. Instead, they rely on secondary reactants to help aid in the synthesis of such films. To synthesize such nanocomposite substrates, cyclic voltammetry is a very commonly used technique where an electrolyte containing a monomer to be electropolymerized is used along with the nanoparticles. Electropolymerized substrates consisting of graphene oxide and polypyrrole, an organic polymer created by polymerizing pyrrole, have drawn much attention owing to their applications in solid-state supercapacitors, biosensing, tissue engineering, and artificial muscle studies. The system is modeled using visual molecular dynamics, VMD, and 10 all-atom simulations, 100 nanoseconds each, are carried out using nanoscale molecular dynamics, NAMD, at different temperatures based on the peak currents and scan rate through the Randall-Sevcik equation. This allows for the analysis of the film as it evolves over a period of 1 microsecond. The system is comprised of one graphene oxide sheet, 50 pyrrole molecules, a water box, and a neutralizing ion concentration for a total of 73,903 atoms. The graphene oxide sheet was created in VMD based off of existing graphene sheets by adding carboxyl and hydroxyl functional groups to the sheet. The pyrrole molecules were similarly created in VMD using the charm topology files. Stability of the GO-PPY nanocomposite is quantified through RMSD, root mean square deviation, and center of mass deviations, whereas the interaction energies are quantified based on the non-bonding interactions such as van der Waals and electrostatics between pyrrole and graphene oxide. Finally, the evolution of polypyrrole films over the surface of graphene oxide is quantified based on the number of pyrrole monomers and number of polypyrrole clusters within 5, 12, and 30 angstroms from the surface of graphene oxide to understand the absorption profile of the pyrrole monomers as it evolves in the polypyrrole. As can be seen by the root mean squared deviation in the center of mass graphs, time is the largest factor in the adsorption rate of pyrrole molecules to the surface of graphene oxide. The number of atoms and van der Waals forces graphs corroborate that time is the major factor. For the residue list table, 5 angstroms away from the graphene oxide sheet is considered to be adsorbed to the sheet. 12 angstroms away is where pyrrole typically forms polypyrrole, and 30 angstroms away is the bulk. This table shows that, although there are fluctuations in the number of atoms adsorbed to the surface, the number of atoms adsorbed and the clusters of atoms at the surface increase with time. The table also shows that pyrrole molecules are staying within the bulk as time goes on, which implies that with more time, even more pyrrole would adsorb to the surface. In conclusion, the evolution of pyrrole into polypyrrole in the presence of graphene oxide has been studied, and it is found that this evolution does follow a specific pattern, which is time-dependent. Both graphene oxide and pyrrole monomers show increasing stability with respect to each other, indicating a stable complex formation. It is seen that between the distances of 5 angstroms and 12 angstroms from the surface of graphene oxide is where most of the trimers and tetramers are formed, which are then adsorbed to the surface of graphene oxide.